Great circles are a really good transition from TNAV to CellNav. And when I was taught it, I was actually taught it as the first part of CellNav, not the last part of TNAV. But I do think it fits in better over here. And why I think it's a really good transition is because you go from having to think about um, individual places on Earth, as in like a single chart and what's going on there, to thinking about the Earth as a whole and how that operates as a single unit. So to review, I got some slightly better tools, but a great circle is just any path along the surface of the Earth that goes for its full circumference. It can't just happen on a portion like this. It can't just be that sweep, because you see how all of this is now sticking off the side. It has to envelop the whole of the circumference of the Earth. Now this is the disc here I have is a little too big, but it's the best I could do. It's a paper cut that I cut the top off of. Yeah, so this has to pass through the widest point of the Earth. And as a result, if you could imagine it as a plane cutting through the Earth, it would hit the center of the Earth every time. Any path that doesn't hit the center of the Earth would count as a small circle. Now, the 2 points that a individual great circle path are defined off of, because obviously there's an infinite number of them, are the vertices, the vertex, the poles, vertices. The elevated vertex and the reduced, declined, I don't know, the lesser vertex, the one that doesn't matter. And what the elevated vertex is it's just the northernmost, if you're in the northern hemisphere, the northernmost point on the curve for the great circle, and then the other one, the lesser one, would be the southernmost. If you were in the southern hemisphere, then the elevated vertex would be the southernmost point. And that's because it's really the only place that you can clearly define as like a starting and an ending point to the great circle. Because while there are an infinite number of great circles, they all have to have unique vertices. So like, if this is my great circle here, I'll try to align it so you can see better, and we're counting this as the North Pole, then this is the elevated vertex. But no other great circle could have that point as the elevated vertex, because if I were to like shift it to the side a little bit, well, now it's just sticking off of the apple. If I were to try to twist it slightly, now over here, this is the elevated vertex because it's closer to the pole. So this is the only one that can have that point as the elevated vertex. Meaning, once you pick this point, you now understand all of the properties of the circle as a whole. And to kind of help you visualize how you would then use it, really quick map. There's the Americas, Africa, Europe. 90% of the great circle sailings that you're going to be following along, because you only ever use a great circle for a really large distance, because that's the only point where it actually saves a meaningful amount of time. But 90% of those sailings will be going a really large distance east-west, for no other reason than that's just because those are the routes that are most commonly being taken. Even if we went over to the Pacific, most of the time people are just headed east-west, west-east, doesn't matter. It's not very often that you would see someone sailing like from North America to the southern coast of Africa, or from Europe to the southern coast of South America, just because there are more convenient routes to take. Like if you needed to go from here to here, you would probably sail to South America and then just go on a route to land. This is totally possible, but it's just there are no routes on Earth that require a full ocean passage that would realistically involve going mostly north-south. They're almost all transverse, going along generally the same latitudes. And so what this means is, so you can imagine looking at the circle here, if you wanted to go on a mostly northwest course along a great circle, you'd kind of have to come over here and slope down along this side, because that's the point where we're clearly going the most southerly or northerly as opposed to east-west. And then if you come over here, you see we're mostly going along the same latitude, like it's only changing a little bit. And you'll see that reflected in great circles a lot too, where usually the track will look something like this. And because this slope, you see it's coming up here and down here, the vertex will be somewhere in the center right there. So you would be taking your starting point, sailing upwards, passing through your vertex, and then sailing back down. What this allows you to do, because like I said, the vertex is the only point that you can clearly identify, or you can identify as a starting point of the Great Circle route, is you can then define your waypoints off of that. Because we need specific waypoints to follow along this route. You can't just say, make a nice, clean, sweeping curve the circumference of the Earth. That's insane. You'd have to break it down into individual steps that a ship can actually follow in a practical sense to then be able to sail along. So the way you break down these waypoints is there's a formula that we'll go over later, where if you have the latitude of your vertex, and then you have a given distance away from that latitude on either side, you can automatically calculate the latitude of the point along the great circle that is that given distance away. So basically, if we have the latitude of this one here, we could say 10 degrees this way would get us this point, and 10 degrees this way would get us this point. 20 degrees on either side would get us there and there. And by the way, this point and this point have the same latitude. This point and this point have the same latitude. 30 degrees would get us there and there. So using the vertex, you can break down the route into a series of much smaller steps that you can then follow straight line Mercator routes between, so that you can actually make this course. The reason why I say this to you in advance, and why I made the point of mostly easterly routes being the most common one, or east-west routes being the most common, and that those routes involve having the vertex in the center, is because you will occasionally get a route where you're going mostly to the south or mostly to the north. Let's say, I don't want to keep skipping pages. Let's say it looked something like that. Well, what would the Great Circle set of waypoints look like this? Well, first you have to find your vertex. And you could think, if this way is north, the vertex is not along here. And this is not the northernmost point, because the curve continues this way and then slowly evens out over there. So even if your starting point is here and your ending point is there, your elevated vertex is not in this direction. Your elevated vertex is right there. Or theoretically, if you were going like this, it would be somewhere over here. So every once in a while, if you are going more north or south than you're going east and west, your vertex will fall outside of your route. Whereas in the vast majority of the cases, your vertex will fall on the inside. You can think of this because if I draw a semicircle here, and you can imagine that the Great Circle continues in a full arc or a full circle on the other side of the Earth, it's just not visible. If you were to try to draw a rectangle where the bottom left corner and the top right corner were your starting and your ending point, anything more east than it is west, or more east and west than it is north-south, would look like this. It would have to pass over the vertex. Anything more north-south than it is east-west would have to look like this. Basically, if the rectangle is taller than it is wide, the vertex has to be outside of it. And if the rectangle is wider than it is tall, the vertex has to be on the inside. And the way you'll know which one you fall under, I mean, by the way, you could technically have it on the outside if you were like this, where it's just a really tiny distance, but you would never use a great circle sailing for something this small. It has to be, you would only ever use it for a route that is large enough that it would have to span over the vertex. And the way you would know this is either in advance when you first get your 2 waypoints, or your starting position and your ending position, because that's the only thing that you're given to start a great circle problem, is just where you're coming from and where you're going to. If you were to just break down what the difference of latitude is and the difference of longitude, and you could see, hey, I'm obviously more north-south than I am east-west, then you know you're in this condition and not this condition. The majority of the time, though, you'll be more east-west, like I said. Another way you'll do it, though, is when you get to the problem, to the formula where you're calculating your course angle, if you're in this case, your course angle will come out as a negative number. When people see that, they usually think that they did the equation wrong, or they messed something up, or they're just like they screwed up. That's not true. It just means that your course angle points to your vertex. So if you're here going here, and you're trying to go this way, but you calculate what your course angle it will point this way. It will say, hey, you're going in the opposite direction than you think you are. That's why it will give you a negative number. When that happens, I'll go into more detail when we get to that video later, but you just add 180 and you flip yourself around to get back to where you were supposed to be headed. Then from there, because you build your waypoints out as starting in the center and moving off to either side, if your vertex is over here and then you start over here and end here, what you're gonna have to do is jump all the way here and then build your waypoint list like that. Meaning, whereas this was a lot easier because doing one equation for 10 degrees this way and 10 degrees that way got you 2 answers, and then 20 degrees got you 2 answers. This time you have to work only in one direction, so it takes more time. But I hope that helps you visualize what you're doing when you actually do the math of a great circle problem. I'm only using the example of America to Europe, or America to like North Africa or Gibraltar or whatever, because that's the most default problem that we were always given, because it's kind of the one that you would expect to be doing most regularly. What you will do over the full course of a great circle problem is you'll take your departure point and your arrival point. You will be trying to identify the curve along here that will actually follow the curvature of the Earth. But the only thing you can do before you get there is you can find the vertex of that curve. So the first thing you would find is that right there, the northernmost point along the curve. And then from there, you could work out to either side to build a list of waypoints that will approximate the path you're trying to produce. Like that. If, however, it's more north-south, like let's say you're doing this, well, once again, the only thing you can do is start by finding your vertex, but in this one, the vertex would be somewhere up here. You would get a negative number for your course angle, which you would have to flip around. This time, because it's actually pointing to the other vertex, I keep forgetting what its name. I think the depressed, the one in the opposite hemisphere than what you're working off of. And you would have to work your way back up from there or work your way down, I suppose, by building the waypoints like that. The only other really confusing thing that happens is when you pass the equator, because on a Mercator chart, a great circle looks like a sine wave, and it changes direction when you hit the equator. So what that will mean is while you are calculating your courses and distances, let's say you're going from here to here, everything would work just fine. You'd set up your first elevated vertex, you would build your waypoints, you're going down, then you would hit a point where suddenly you're at the equator, and it will be exactly 90 degrees from your vertex if you want to check, because obviously this is the most northern point, and this is 180 degrees away from it, so the halfway point has to be 90 degrees. And then suddenly the courses you're following will change into the other direction. But the math will all continue to work the same, so you don't have to panic and get confused. You just continue doing what you were doing. You're just changing the direction that you're curving as you do it. And obviously now you're increasing into the other hemisphere. All right, I think that's everything I wanted to go over. This is just, before we actually begin doing the work of it, a basic idea of what you're actually aiming towards getting, because a lot of people just know that like magically in the end they will have a great circle, or they'll have a path they can follow, and I want you to be able to visualize how you're actually doing that by first starting with the vertex, which is the most polar point of the great circle path, so the one closest to the pole. Specifically the pole that you're on the side of. If you were over on the southern hemisphere, this would be your most polar point, your vertex. And then you're just starting from there, finding the slope around it that you can actually follow to keep the shortest route. And once again, it is the shortest route because if you imagine this as a plane that's perfectly cutting through the apple and hitting the center, technically here to here straight across would be along that plane, just cutting into the surface of the earth, which isn't an option, but following over the top of the earth while staying on that plane is the closest you can get to that straight line.